All right. Well, let's get started. So Alberto is gonna give us a talk about QuantumToolbox.jl, and then we should also just put in a reminder for something for after. So we'll continue to keep people up to date about organizing maybe some quantum specific hangout after the session. But Alberto, take it away.
Thank you. Hello, everyone. I'm Alberto Mercurio. I'm a postdoc at EPFL in Switzerland. And today we'll talk about QuantumToolbox.jl, which is a framework similar to other frameworks like QuTiP in Python, Quantum Optics in Julia, and many others. And why simulate open quantum systems? Let's take this example where we have a cavity field and an atom inside this cavity field, and we want to describe the interaction between the two. But not only, we have an input drive field, the blue field, and we want to study the scattered field outside the cavity. This is what we studied in a recent paper on Physical Review Letters 2 years ago, studying the spontaneous Raman scattering in the ultra-strong coupling regime. And what you do usually is that you study the time evolution of the density matrix, which is an open quantum system now. And for example, rho is the density matrix of the system, H is the Hamiltonian, gamma J is the dissipation rate of the jth dissipation channel, Cj are the so-called jump operators, and D is the lambda dissipator, describing the dissipation towards an environment, an external environment. So during my PhD, I was using QuTiP. You may know this package is a very known package in Python, probably the most open source package used for open quantum systems. But for simulating my kind of research topics like ultra-strong line matter coupling and many other research areas, I needed something more. So I was looking for not only something more powerful, but also with GPU support, which was like starting to increase in popularity, and other features that QuTiP didn't have at that time. Now QuTiP version 5 has also GPU support, but whatever. But at that moment, I was searching for something more powerful. And I was starting using handmade Python codes with GPU support like QPy. I don't know if you know many of these packages, but failing on the difference in performances, but also in hard code, because I had to write by hand many codes which were not very easy to write and whatever. So I started to switch on something different, and that's why I found Julia, and I started to write by hand, basically all the lines code similar to the QuTiP syntax, because that was the syntax I got used to, with way more powerful simulations, but also GPU support and many other features. And that's why I started writing Quantum Toolbox. The basic idea of Quantum Toolbox is very simple. Everything is around the quantum object. A quantum object has three fields. You have the data field, which basically embeds the linear algebra field object of the system. You may know that quantum mechanics is heavily based on linear algebra. And so basically you can express an operator as a matrix, a state as a vector in the truncated space, of course. And so data has exactly this purpose. And the data has no limitation on the type of the array. For example, data can store a dense array, a sparse array, a GPU array, both dense and sparse, static arrays, and you can invent one of your abstract array, and Quantum Toolbox should support it. And then you have the type field. The type field, of course, includes the information about the quantum object itself, whether it is a cat state, a bra, an operator, super operator, and many other type of quantum objects. And then dimensions. Dimension is a field that is useful when you have a multipartite system. And basically, it embeds all the information about the Hilbert space dimension for each subspace, such that, for example, when you want to perform the partial trace, you want to keep track the local Hilbert space dimension for each subspace. And with this in mind, then you can build all the time evolution solvers, linear algebra operations, and utility functions. For example, for the time evolution solvers, so you can solve the Schrödinger equation, the master equation, Monte Carlo quantum trajectories, stochastic master equation, and Schrödinger equation, low rank dynamics, which is very useful when your system is almost pure. And you can also compute steady state without performing the entire ordinary differential equation. You can also use a hierarchical equation of motion for simulating non-Markovian environments. This is actually performed using eon.jl, which is another package written by ITE, another maintainer of the package. But the hierarchical equation of motions are heavily dependent on QuantumToolbox.jl and many other dynamical solvers. I will show you later the dynamical shifted Fock, which basically is very useful when you want to simulate strongly driven open quantum systems. And you can also have utility functions. You can compute entanglement of a system. You can compute the correlation function, the emission spectrum, eigenstates, and many others. So, but why Julia? I already explained you why. When I was looking for something more powerful, Julia had all the ingredients that I was looking for. So we have just-in-time compilation, support to GPU acceleration, native distributed computing, which is very important for open quantum systems. You will see later how easily we can simulate quantum trajectories on a cluster with just one line of code, basically, and then multiple dispatch. Thanks to multiple dispatch, we can basically simulate a system both on CPU, on GPU, with just one line change of code. And so we have matrix vector multiplication, and we see that on GPU, it takes almost 290 milliseconds for the sites that I chose. And by just adding these two lines that converts the matrix into a GPU object, you basically have way more performances. And so let's study a bit the basics of QuantumToolbox.jl. So here you see a simple code that generates the Liouvillean. The Liouvillean is a super operator that basically embeds all the information of the open quantum dynamics. And in this case, you can see, if you know QuTiP, the Python package in QuTiP, you see that the syntax is almost the same, except for a few changes, for a few differences, like the dagger is not .dag, but there is the adjoint symbol in Julia. But aside from that, the syntax is exactly the same. This means that all the people coming from QuTiP in Python may change language with a little effort of just changing a few things. And look how easy it is to just make it support GPU support. We just import CUDA, of course. We have to import CUDA and just convert the annihilation operator, the bosonic annihilation operator, into a quantum object, but in the GPU, stored in the GPU. And let's make it practical. For example, I want to simulate the master equation of an open quantum system. And let's do it with the driven James-Cummings model. So I have a single mode cavity field described by the operators A and A dagger. I have a two-level system described by the Pauli operators sigma z, sigma plus, sigma minus, and other Pauli operators. And then I have a drive. So this last term is the drive term. I am in the drive frame such that my Hamiltonian is time independent. That's why I have delta C and delta Q, which means they are the tuning with respect to the drive. So everything is time independent. And I had some dissipators. What I had a single photon dissipation. My cavity may lose a photon outside in the environment. And the environment may have some thermal population, may have some temperature. So that's why I have this N thermal here. And just because the environment has some finite temperature, I also have some incoherent pumping inside the cavity. So I had an additional jump operator, a dagger. And then I also describe some photon dissipation. So the photon itself can decay without emitting to the cavity, but rather emitting into the environment. And this is these are the lines of code used to simulate the master equation. we can see that we define the Hilbert space cutoff of the cavity field. The cavity is an harmonic oscillator, so in principle should have an infinite dimensional Hilbert space, but we are in a computer, so we have finite memory, unluckily. So that's why we have to define a cutoff. In this case, I define a very large cutoff, 150, because we are gonna pump strongly the cavity and to see what happens. And then I defined an annihilation operator thanks to the tensor product, sigma minus, sigma zero, all the Pauli operators. I defined Hamiltonian, the collapse operators as a list, the expectation value operators, same as QuTiP. So I want, for example, to compute the number of photons and sigma z as a function of time during the time evolution. I define my initial state, the list of times at which I want to simulate my master equation, and compute the expectation values, and that's it. And then I compute the master equation using MESOLVE, just like QuTiP. Most importantly, in the time list, I define some dt, some time interval, but the integrator doesn't have anything to do with the interval because it's an adaptive integrator. The interval is just needed for if you want to compute the expectation values. So the expectation values are computed exactly in the t-list that you put. This means that the integration fidelity doesn't depend on the time interval that you put in t-list. So that's it. For example, here we see the photon number as a function of time, and they are quite a lot. They are more than 40. And on a CPU, it took 1 minute on my laptop, but you can easily run it on GPU with 2 lines of code, and it runs in 4 seconds. You can also do Monte Carlo quantum trajectories. What are Monte Carlo quantum trajectories? You basically study the open quantum system dynamics, but in another framework, in the framework of quantum trajectories. Now we don't have anymore a density matrix that evolves, but we have a pure state, many pure states that evolves each one with each trajectory, each a quantum trajectory. And now it is a random process. So each trajectory, which is an evolution of a pure state, at some point may have a quantum jump. So a jump occurs, and then keep evolves again. And if you average among all the other trajectories, then you get exactly the same physics of the master equation. So they are 1-to-1. And so, for example, you can compute the probability to jump, which is again a random process at time t, which depends on the collapse operator and the pure state at time t. And then when a jump occurs, your state changes brutally in a how to say, in an indirect way. And this is the code used for running Monte Carlo quantum trajectories. I import the random package, just to show you that I can also set the random number generator in the case where I want to exactly reproduce the same dynamics, even if I run it within 2 months or after 6 months or 1 year, or in another laptop, another machine precision or whatever. I want to have exactly the same dynamics, which is again a random dynamics in this case, and the random number generator is very useful in this case. And here I run 50 trajectories, and this is the simulation of the photon number. And as you can see, they don't exactly match the master equation. Why? Because they match the master equation in the limit of infinite number of quantum trajectories. So in the limit of infinite number of quantum trajectories, the 2 lines converge. And here we just an additional argument, which is ensemble alg, and I use ensemble distributed. I'm able to distribute all these trajectories on a cluster. So with just one additional argument, I'm able to increase the performances of my simulation by at least 1 order of magnitude for sure. And this is very important because this means that I can run my simulation on my laptop. Then I decide to increase the Hilbert space dimension or something else that makes the simulation much heavier. And what you do is just copy, paste the code in the cluster. For example, if you have a Slurm cluster, and that's it. Everything is already working. So the quantum trajectories can be seen as a photon absorption from the environment. So can be seen as the environment as a detector, and this detector clicks. So a quantum jump occurs when the detector clicks, and this can be seen as a photo detection. But there is another way to describe losses or in general measurements. For example, on the left side, using, for example, homodyne detection. In this case, here I have a cavity. There are some photons in the cavity. If the photon escape from the cavity, this photon is now mixed with a strong local oscillator, a local field, which is very strong. And then using some statistics, you can reconstruct the state of the cavity using this homodyne method, which we don't care to investigate further. But the important thing is that the two methods are describe exactly the same process of losing a photon, but analytically and numerically, they are described in a different way. In this case, we have the stochastic master equation. I'm not here to explain you how it works, but basically now it is not random but stochastic. So we have here the last term is dw, is a Wiener process, so it's exactly a stochastic process. So we don't have to use the ordinary differential equations, but we use stochastic differential equations. They are different. And we can basically also simulate homodyne trajectories very easily on Quantum Toolbox. Like in this code here, where I define the operator that acts as the detection operator, usually is the bosonic annihilation operator, because it's related to the photon loss. And I define the other two operators, which was the bosonic creation operator and the sigma minus, as additional losses that are not tracked by the homodyne measurement. In this way, I again run the simulation with the SME solve, which means the stochastic master equation solve. And we can see again the simulation, and they match the master equation case, which is important. And most importantly, I can also extract the homodyne current, which is what exactly experimentalists measure. And here you can see the average of the master equation in the blue line, and in green you see the measurement over 32 trajectories of homodyne current trajectories. Another important feature is that QuantumToolbox.jl integration methods use differential equation.jl, so which means that they use a very powerful ecosystem and very, very well tested. And for example, one of the features of differential equation.jl is that it supports callbacks. So you can add a function that operates only if a specific condition is matched. And in this case, that's why I implemented the dynamical shifted Fock algorithm. What are the basics of dynamical shifted Fock algorithm? Imagine that I have a harmonic oscillator, and it is strongly driven. This means that most likely the field is a coherent-like state. So is a coherent-like state in the phase space, which may have a very large photon number, but still localized in phase space as a coherent state should be. This means that if you simulate in a standard way the master equation, you should, given the high photon number, you should simulate with a high cutoff number, which means that your simulation becomes very slow, and as we have already seen before. But we can do another trick. We define a very small Hilbert space dimension, which depends on the quantum fluctuations around the coherent state, and we just move this frame around the phase space depending on the coherence of my state. This means that this method can efficiently simulate coherent-like state, almost coherent-like state, which were basically impossible to study if not like mean field theory or something else approximate. But here you can study it, you can simulate numerically exactly. And the basic principle is very simple. I just had a callback in the simulation that checks the coherence of my system. If the coherence is larger than some threshold, then I apply the displacement operator inverted. So imagine that I have exactly a coherent state, so I have alpha, and if this alpha increases more than a threshold, then I apply the inverse of the displacement operator, and what I get is exactly the vacuum. So I'm mapping again a coherent state into something that has way lower energy in this new frame, of course. And what if the state is not exactly a coherent state? Well, what you get is something which is not exactly the vacuum, but the coefficients, if the state is coherent, like almost coherent, the coefficients decrease exponentially as you increase the energy in this new frame. So that's why you can simulate the system with a very small Hilbert space dimension. And just a brief introduction about automatic differentiation. I started to implement it just recently because it's very important for open quantum systems, quantum optical control, and many other features. And here I show you just a few basics. Imagine that you have a set of parameters, which we call theta 1, theta 2, and theta n. And my dynamics, my Hamiltonian, my collapse operator depend on this set of parameters. For example, drive amplitude, the tuning, or whatever. And so this means that if I want to compute the expectation value of an operator at time t, this number depends on theta as well, because rho depends on theta. And imagine that now I want to compute the gradient of this quantity. For example, if I want to do gradient descent because I want to descend the gradient to find the minima, local minima, or something like that, the first thing I may think is using finite differences. So I basically discretize my derivative, and I have I have an approximation of my derivative, but I may say, okay, it's numerical. But the problem is that as soon as you increase the number of parameters, finite differences are not very efficient, and also they suffer from numerical instabilities and tolerances. That's why finite differences are not the option, especially in quantum simulation. And that's why you need the automatic differentiation, which basically what does is that is like that the compiler already knows the derivative. Like in this simple case of Zigodi.jl, which is a package of the automatic differentiation, you can see how the derivative of a simple function is exactly compiled as it should be, without any finite error differences or whatever. And let's make an example. I have a driven harmonic oscillator, and I know analytically that in the limit of time approaching to infinity, so at the steady state, the photon number is written here in the top. Let's get theta, the parameters, as the tuning and the photon and the drive amplitude. What I get is that the analytical formula for the gradient is written here. But now how to do it numerically? Imagine that I don't know the analytical formula. I have a system way more complex. How do I do? In Quantum Toolbox, we can take advantage of another package of the SciML ecosystem, which is SciML sensitivity, which basically allows you to differentiate an ordinary differential equation. And the main difference is that now I have to define my Hamiltonian as a Q_, where you can see that I define two terms. The first term is a dagger A, and the dagger A multiplies delta, which is the tuning. And delta is a function, and this function has inside the parameter. Because again, I want to differentiate on the parameters of my system. And the same thing happens to A plus a dagger, which is the drive. And the coefficient of the drive is again another function which takes another parameter. And now I define the collapse operators, the Liouvillean, the initial state. And this function here is a function that just performs the master equation. So defines the time list and performs the master equation of the Liouvillean, initial state, the t-list, and the parameters. And most importantly, we have to set the sense_alg argument from SciML sensitivity to have better performances, basically. And then, basically, we integrate for a sufficient long time and we then return a DAG array at the last state. So it's not exactly a steady state solution, but if we integrate far enough, we get more or less the same number. And then we use zigoti.gradient to compute the gradient of this master equation. That's it. And we can compare the derivative of a DAG array with respect to delta, to the tuning, and we compare it with respect to the analytical solution, and as you can see, they match exactly. And to conclude, I can show here some performance comparison with other packages like QuantumOptics.jl in Julia, QuTiP written in Python, and Dynamics still written in Python that uses JAX, which is a powerful package in Python also for machine learning stuff. And as you can see, QuantumToolbox.jl is very powerful. Of course, also QuantumOptics.jl is very powerful because both of them are written in Julia. And at the bottom, you can see the CPU simulation and GPU simulation as a function of the Hilbert space dimension. And again, you can see that QuantumToolbox.jl is basically the most powerful in this regard. And that's it. I invite you to see our webpage. The documentation is still ongoing. So if you think that there is some feature which is not documented, please open an issue or contact me. We can for sure add this documentation. And I also thank Ite Wang, which is the other maintainer maintaining the QuantumToolbox.jl package. And I thank you for the attention and invite you to see our release paper on arXiv. Thank you.
Questions? Yeah.
Hi, thank you for your presentation. I'm especially interested in the automatic differentiation part and curious about how it's actually implemented. So you use Zygo, which is reverse mode AD, and to make it work, do you just store the computational graph and revert at each step for your time integration solver, or it is some more analytical method, or is a combination of both?
I'm not an expert on that. I just asked myself, can I make it support automatic differentiation? And after a few pull requests on both IML sensitivity.jl and many other things, I managed to make it work. But I know that there are many methods. For example, here you see that the method used is the joint method. I don't know the details, but basically you back propagate your simulation in some way. If this is what you mean.
Okay, I see. So,
but if you want some information, there is SciML sensitivity package, and there is all the information about how to differentiate an ordered differential equation. It's very detailed, and you can understand how they do it. There are many other methods for that.
I see. Thank you.
Others?
Have you looked at GPU.jl? They have some tools for doing parallel ODE solves.
I started using it a few years ago, but then I realized that for quantum systems, especially open quantum systems, at least on my knowledge, it is not so helpful because DFQ GPU is useful when you have many small system of differential equations and you want to distribute them on the GPU. But in the open quantum system case, your matrix dimension, so your ODE dimension is usually large. So I think that if you look at their documentation, they distinguish between these two cases. They distinguish between the large ODE case, where you have to convert the matrix itself into a GPU, and the small ODE case, but many trajectories, and that one you can use DFQ GPU. But I never used again since 2 years, so maybe we should give a look again.
Yeah, thank you for the nice presentation. I was wondering if the toolbox has some support, or if there are any plans to maybe have the option of swapping out some of the backends. So I'm from a tensor network background, and so of course like these kind of things with maybe matrix product states or these kind of methods that have approximate solutions for these integrations could also maybe be helpful to push the numerics further. Is this something you've considered, or maybe can you comment a bit on this?
You mean the direction of other ansatses like tensor network or whatever? Not now, but I think that I was starting thinking about it. It's not so simple, but if you have an idea, we can discuss later and maybe something interesting may emerge.
Yeah, thank you.
All right, let's thank our speaker again.
Thank you.
And